Hello and welcome to this tutorial on the induction machine and doing some power calculations around it. These sorts of things are often given in exams. They are quite straightforward questions, and so we're just going to quickly go over those in today. So let's say we've got a problem and we've been given, let's say it's a 75 kilowatt machine. We'll say the line voltage is 400 volts, the frequency is 50 hertz. We say we know the efficiency of the machine and we'll call that 93% efficient. We know that the rotor speed is moving at 975 RPM. The machine has got losses at the rated speed of 5%. We know that R1 is 0.33 ohms, and it's a 6-pole machine. So these are the sorts of things you get given in a question. Now, what can we understand about this machine from what we've got given? The first thing we can figure out is how efficient the machine is. We know that efficiency is power out over power in. We know the output power, we know the efficiency, so we can work out the input power. The input power would be the output power divided by the efficiency, which is 75 kilowatts, and the efficiency is 93%, which gives us an input power of 80.65 kilowatts. That's one of the first things we can understand. As an induction machine, we always want to know what the slip is. To find out the slip, we need to know the rotating speed of the machine, which we have, and the synchronous speed of the machine, which we don't have. Its synchronous speed of the machine can be found out from the frequency and the number of poles. So, the synchronous speed of the machine, NS, is 120 times the frequency over the poles, which is 120 times 50 over 6, which equals 1000 RPM. Some people prefer to work in radians, so we can divide that by 9.54, I think it is. I use 9.6 is close enough. That gives us 105 radians per second. Similarly, this value down here, the speed, that is the same as 102 radians per second. What else? We can go back. We need to, as I said, we need to understand the slip of the machine. And as we know, the slip is the speed of the synchronous speed minus the rotor speed over the synchronous speed, which is 1000 minus 975 over 1000. And again, to remind you, it doesn't matter whether you do this calculation in RPM or in radians, provided you use the same values all the way through, because it is just a ratio. And that comes down and that gives us a slip of 0.025, which is 2.5%. What else can we find out about this machine? We can find out what its power factor and everything like that is going to be. How much real power is it consuming? How much reactive power? How much apparent power? So we can do those quite simply. We know what the real power is. Here it is here. So, and we know what the power factor is. Do we? No. We've got the poles, resistance, loss. No, we haven't got the power factor there. We'll pick a power factor. Power factor 0.85. Okay. So what we can therefore know is we know that the apparent power is the real power over the power factor, which is 80.65 over 0.85, which gives us 94.88 kVA. We can go through and solve for Q. The Q of this machine is the apparent power times the sine of the angle. We don't know what the angle is yet, but we do have the power factor. So we can take a slight detour over here. We know that the angle is the inverse sine of the power factor, cos -1, 0.85, and that gives us 31.8 degrees. We can then take that and insert it into there. Sorry, that should be, I've written that out wrong. That should be 94.88 times the sine of 31.8, and that there comes down, gives us a Q of 49.98 kVAR. What else can we easily figure out here? We haven't got torque, so let's go through and find, we've got enough information there to find out what torque is. Torque, as you know, is the power out at the rotor divided by the rotational speed. The power at the rotor, we already know, is 75 kilowatts. The rotating speed is 975 RPM, which is 102 radians per second. And that gives us a torque of 734.6 Newton meters. At that point I've run out of paper, but that's enough to go through when you're given these sorts of this sort of information, of how you can go through and immediately deduce a whole lot of other things about it. If you know efficiency and output power, you can work input power. Those are fairly straightforward calculations. Finding the torque, that's quite straightforward. The real power, apparent power, and reactive power, those are all straightforward calculations, as is the slip and that sort of stuff. So, my email. Thank you very much. Look forward to seeing you again, and thank you for watching.